Today we are going to see the size of a structure variable. So what we know here is that the size of a structure is the sum of all the data member sizes. But the size of a structure is not always equal to the sum of size of individual member. This is because of the padding which is added by the compiler to avoid the alignment issues. So what is this padding here is for the processor to access the contents fast. So the compiler will be adding what is called as padding. So padding is added not in all the cases. It is added when a structure member is followed by a member with a larger size or at the end of the structure. We'll see some examples to show what is the meaning of this. And these bytes which are added, extra bytes which are added as padding, are called as the slack bytes. In a 32-bit processor, the processor can access 4 bytes at a time, which means that the word size is 4 bytes. In a 64-bit processor, it can access 8 bytes at a time, which means that the word size is 8 bytes. And this structure padding is used to save the number of CPU cycles. Now, if you consider a 64-bit system, the size of integer is 4 bytes, size of character is 1 byte, and size of any pointer is 8 byte. 8 byte because it's a 64-bit processor and 1 byte is 8 bits. So 64 divided by 8, which is 8 bytes. So to refer one memory location, 8 bytes are required. So since your pointer holds the address of any memory location and memory location requires 8 bytes, so the size of the pointer type is 8 bytes. And we already know that pointer size does not depend on what kind of data type they are pointing to. It depends on the processor, whether it's a 64-bit processor or it's a 32-bit processor. Now, different compilers will have different alignment constraints as C standards state that the alignment of the structure totally depends on the implementation. So we'll see some examples to show this. Let us see the first example. Suppose inside the main I have a structure A with the members integer x, double z and short int y. So now we have assumed that this is a 64-bit processor on which we are writing this and executing the program, and we know that the size of integer is 4 bytes, and since the processor is a 64-bit processor, so x is taking only 4 bytes. The next variable is double z, which is which requires 8 bytes. So since the size of z is greater than size of x, so z will be stored in the next word. And one word in case of your 64-bit processor is 8 bytes. So x takes only 4 bytes. So the remaining bytes will be left unused. And z will be taking the next continuous word. So which is after 8 bytes of x. After the starting address of x, between x and y, z, the address will be varied by 8. And the next is the short int y, and we know that the size of short int is 2 bytes. And this 2 bytes will be definitely has to be stored in the next word. And since it is only 2 bytes, the remaining 6 bytes will be not used by this structure A. So these last bytes and bytes which are between x and z, we call them as the slack bytes. The size of integer is 4 bytes, double is 8 bytes and short int is 2 bytes. The sum becomes here 14. But if you run the same program on the 64-bit processor, you will get the output as size of structure is 24, because after this 14 bytes, so this is again 4 bytes, so 14 plus 4 is 18, and this is 6 bytes, which is 24. So this is why you are going to get the output as the size of structure is 24. Now let us see the second example. So inside the main I have declared a structure B and the same kind of variables, but I have stored first the double variable and then the integer variable and then the short variable. So in this case the first double variable will be requiring 8 bytes, and the next variable, which is an integer, it requires only 4 bytes. So this double, it takes one word completely, so the next word onwards your x will be stored. So after integer, if you observe now here, it's a short int y. So we know that short int y takes only 2 bytes and it is less than the size of x. So it can be accommodated in the remaining 4 bytes. So x and y will be stored in the same word of the memory. So last 2 bytes will be called as the slack bytes, or padding of 2 bytes will be taking place. So total size of the exact size of the variables is 14 and the 2 padding bytes will be taking totally 16 bytes. Let us see the third example. Inside the main, here the structure C is declared like containing the members double z, short int y and the integer x. And double z, as usual, it requires 8 bytes. So it takes one word of memory. And short int, it requires only 2 bytes. So y will be stored in 2 bytes of the next word. And the next variable is integer x. It requires 4 bytes. Since x is requires 4 bytes, so between y and x there will be 2 padding bytes. So again the size of the structure here is 16 bytes. So here from all the 3 examples, what we can make a note here is C language does not allow the compilers to reorder the structure members to reduce the amount of padding. So in order to minimize the amount of padding, the structure members must be sorted in a descending order, which is shown in the case 2. Now the same program, we are going to run it and check it out. So structure A, we have declared the integer x, double z and short int y. In structure B, we have declared double z, integer x and short int y. And the structure C, double z, short int y and integer x. After the declaration of the structure variables, I am printing size of structure A, percentage %LD, size of structure A. Similarly, the size of structure B and C are printed. Let us run and check the output. So you can observe that the size of structure A is 24, B is 16 and C is 16. Now to make sure that whether the slack bytes are between x, y in the second case or after y, you can print the address of the variables by creating one structure variable and printing the address of x, address of y, all those things. And similarly for the case 3, you can identify where the slack bytes are by creating one structure variable and printing the address of the members of the structure variable. Now let us see, if I change this structure to a union, what will happen? Union If you run it and see, it should give the same value for all the three union variables. And the size of union, as we know that it is the size of the largest data type. So in this all the three cases, the size of the largest data type is a double data type, which is 8. So the answer should be 8 in all the three cases. Let us run and verify it. So you can observe that the size of union A, B and C all are 8 bytes. So in case of union, the order of the numbers does not change the output. Thank you.